Hello, and welcome to our section on electrochemistry. Great big sounding word, but all it means is the study of the interchange between chemical and electrical energy. And that can happen, two different situations can happen when we talk about electrochemistry. First, we can have a chemical reaction that produces an electric current. And we've been talking about oxidation reduction reactions. Those are the kinds of chemical reactions we're talking about using. When we use those, we can produce an electric current from that. These are examples of this would be what we call galvanic cells, and that's what we're going to discuss in this section is galvanic cells or batteries. This is what you guys know them as. The other situation, and in a couple of sections we'll be talking about this situation, is where we take an electric current and we use that to produce a chemical change. That's called electrolysis, and we'll talk about that in a couple sections. So to understand how a redox reaction can be used to generate a current, let's look at this example, this reaction between permanganate and iron. And I'm going to break that up into its two half reactions. So here I wrote the reaction for you. We have the reduction half reaction with permanganate and the oxidation half reaction with the iron. When that occurs in a solution, electrons are transferred directly when the reactants collide. When the permanganate and the iron molecules collide, we get a reaction directly. But no useful work is obtained from the chemical reaction when these are all just mixed in one beaker. So how can we harness the energy? And the key is this: we have to separate the oxidizing agent from the reducing agent. Here we're putting the oxidizing agent in this beaker and the reducing agent in this beaker. We're separating them. So we require the electron transfer to occur through a wire. And that wire is right there. We have our wire. The electrons are going to have to travel through this wire to be transferred. The electrons are going to be transferring, I can write this direction down the wire, because they are going to be going from our reducing agent traveling to our oxidizing agent, and thereby we can get work happening. We're going to get a current produced in this wire by the electron flow. Now, if I am to set this up exactly as I have drawn it here in the lab, and I have these two beakers and my electrodes and I have the wire, nothing will happen. Why? So if we set this up where we're trying to get electron flow like this, what is really going to happen? This beaker is going to become increasingly positively charged as electrons are leaving, and this one will become increasingly negatively charged as electrons are entering. We're going to get a buildup of positive charge over here, a buildup of negative charge over here. This can't happen because it would require a huge amount of energy to make it work. So this actually does not occur. These electrons do not flow when it is set up this way. So what could we do to make the electrons flow? What could we change so that this system will generate a current? So what we need is some way to transfer these ions between the two solutions. As we are building up positive charge here, we need to be able to let those positive cations flow this way. And as the negative charge is building up here, we need to allow these ions to be able to flow this way so that we can continue to maintain our current and that electrons can transfer through that wire. So there's a really easy way to solve this. We call it a salt bridge. So our salt bridge allows for that flow of ions to occur. We get our positive ions being able to flow here, the negative ions being able to flow there, so that we don't have a buildup of positive or negative cations and positive or negative charges here, and we can get a flow of electrons through our wire. This salt bridge is basically a glass tube that is filled with a very strong electrolyte, so it minimizes the mixing between the two solutions, but it allows the flow of ions between them. There is also another setup, and let's look at that on the next frame, that looks like this, where a porous disc right here would contain that strong electrolyte that is able to discharge those ions between the two solutions. So let's maintain these conventions that we've been using and look at a battery, a galvanic cell. Put the pieces all together here. So we are looking at having our reducing agent in this solution here. Remember, the reducing agent is losing electrons through the wire. So it is losing electrons. It's the reducing agent. Therefore, it is being oxidized. Oxidation is occurring over here at this, what we call the anode. Oxidation always occurs at the anode, and this is just an easy convention to help you remember. They both start with a vowel. Anode is where we see oxidation. If we look at the other side here, the cathode, we label the cathode the place where reduction occurs. Those are both consonants. So cathode, we see reduction. The anode, we see oxidation. Where reduction is happening, remember, that is where our oxidizing agent is in the solution. And this is the setup for a galvanic cell. Make sure you understand that the cathode is where reduction happens. The oxidizing agent is the solution here. And the anode is where oxidation happens, and that's where we have our reducing agent. We must have a salt bridge or a porous disc through which those ions can be exchanged so that we can have our current of electrons flowing through the wire. So to review, we have just looked at what a galvanic cell is, an electrochemical battery. And it is powered by a redox reaction where we separate the oxidizing agent from the reducing agent. We have to separate them so that we can get work done. And electrons then must travel through the wire from the reducing agent to the oxidizing agent. That is called the galvanic cell. We are using that redox reaction to produce an electric current. If you would like to do some advanced proficiency, look up some examples of a galvanic cell using reagents other than the permanganate and the iron that we were using. Identify the anode and the cathode, the oxidizing agent and the reducing agent in those reactions, and show what's going on. And I look forward to seeing you in class.